Again, this one started with me watching some festival titles on Behance, I think, and for the hell of it, again, I cannot remember where they came from, what they were. They were dark, red, they were beautiful, and they had some close-up shot of some, I think, 3 or 4 tangled wires. And I thought, why not put a twist on it and, well, twist them. So, what we're going to build today is twisted wires in Vellum. And to start out, I'll drop down a grid, dive in there, and set my grid up to be oriented along the YZ plane, like this. Zoom out a bit, style back the size to 1 and 0.6 respectively. Let's move it to the side, set it up to have only 1 polygon, 2 rows, 2 columns, like this. And I'll use this and a duplicate of this grid to span wires in between them. So let's duplicate the grid just by using a transform, moving it 2 along the x-axis, like this, so it's on the other side. And then dropping down a scatter, where we wire in the first grid, and we'll have a total count of 96 points, and leave the rest of the settings as they are. Let's copy this, and wire in the transformed grid here, and we will just change the global seed to 1, so the points are oriented a bit differently than on the first scatter. Next, as we have an identical point count on both planes here, on both grids, let's use a point triangle and connect them. Wire in the scatters like this, and we're going to use 3 lines of vex to just span a polyline between points with identical point numbers coming in through the first and the second input slot. So let's get the second input slot's points position, call this one vector endpos, and it should be equal to the points position coming in through the input slot 2, that's the one with the ID 1. We are going to look up the position, capital P, on the point with the PT number. That's the same as the one of the point coming in through the first input slot here. Next, we're going to create a new point. That means we basically copy over the point from here to there. By using the add point function, we're going to add that point to our geostream coming into the first slot, and at the position we just read out like this. And finally, we're going to create a primitive using the add prim function on our main geo, a polyline between point with a point number and our newly created point like this. Highlight this here, and we now created a bunch of wires. Save this. Now if we switch on point display, we can see that those wires only have 2 points, which is a bit sparse for a simulation. So let's drop down a resample, wire this in here, and set our length to something rather small. 0.0075 is what worked well for me, so really dense points here on those lines. Also on my resample, I want to scroll down a bit and check curve view attribute, which just writes in an attribute on each of those points on the curve, starting on the first point with a 0 and ending on the last point with a 1. The reason why we're going to need this is we will use it to separate the first and the last point from the other points and put them in a separate point group that will then be pinned, so those wires will stay attached to their original points that we scattered on there. Let's do that with another point triangle, and we're going to check if our curve view attribute that we generated is either equal to 0 or if our curve view is equal to 1, so if it's the first or the last point, then we'll add it to a group called pin. Let's just highlight this, middle mouse on this, and yeah, we've got 96 times 2, 192 points in a pin group. Also, I just want to duplicate this here and paste it one more time. This time I only want to check if we are on the first point, so the point with the curve view of 0. Then we'll add it to another group called start, which we'll later use to only rotate those points. So yeah, that worked too. For later, what I want to do now is prepare another attribute and call it R-scale. Because what I want to do later in the Vellum simulation is I want each of those wires to have a different rest length, so they have more or less sag and not all fall down uniformly. And for that, I'll just prepare another point attribute using another point triangle. Just a float, call it R-scale for rest length scale. And let's use our random function, but this time not using the point number, but the primitives number to which the points belong, plus a little seed. So now each point belonging to the same primitive has the same random number attached to it in the R-scale attribute. Next, let's twist those points. Let's twist those start points using a transform. Wire this in, highlight it, and set it only to the group start. And then I'll just put a little expression in the first rotate dialog. So I want to do $ff, which is the current frame number, -1, so we start at 0, the first frame, times, let's say 2 in our case. Let's have a look at this. yeah, now we have only those starting points twisting here, which looks a bit weird, admittedly, but we'll get there. Now, finally, let's configure Vellum using a Vellum constraint, wire in our transform here, and let's set the constraint type to string for now. You could use hair as well, but string worked fine for me in this case, and it's a bit more lightweight. So let's check mass and thickness, and for the thickness, I want the thickness to be half of the value that I dialed into my resample here, so half of this one. So let's just right click on this, go to copy parameter, then in the Vellum constraints just paste the parameter as a relative reference and then multiply it by 0.5. So now we have exactly half of the length of our resample. Also, what I found helpful is increasing the drag. That's just dialing in values for the simulation later, so normally you'd have to run a simulation first and then check and then iterate through those values. Next, yes, I want to pin a few points to the animation, those that are in the pin group, and I also want them to follow the animation, that is the rotation. Next, I increase the damping ratio for the stretch stiffness, and also increase the bend stiffness to 1, and the damping ratio to 0.05, like this. Now, let's attach the Vellum solver. And let's drag this down a bit, because we're going to work on these constraints here a bit. And the main thing I want to do with those constraints is I want to scale their rest length individually, depending on the R-scale attribute that we created up here. And for that, I'll drop down another point wrangle, wire in my constraints in here. Let's just pipe them back to the Vellum solver like this. And then from this point wrangle where we set the scale, let's wire this in the second input slot here. And within the VEX code, all I want to do is just look up the R-scale attribute from those points coming in here, and write them on those points on the first slot. Like this. However, when we middle mouse on this here, we can see that the rest length is a primitive attribute. So in order to be able to wrangle this using a primitive wrangle, let's promote our attribute, the R-scale, from a point to a primitive. So now when we middle mouse on it, we can see we've got an R-scale here as a primitive attribute, and our rest length here. So finally, we'll drop down a prim wrangle. And in here, we will just multiply our rest length times our R-scale, like this. Highlight our Vellum solver, and then let's simulate this. Let's stop this and check again. So in here, let's highlight our geo-wrangle, go to the prim attributes, and yes, we have different R-scales, different rest length. However, the simulation is behaving a bit weirdly, so let's dive in the Vellum solver here, and let's increase the substeps to 8, and also lower the constraint iterations to 8, and let's resimulate this. And yeah, that looks a bit more promising. So the only thing left here that I could do is, when I zoom in, sometimes I see some jaggies in here. I mean, in this case, it's fine. What I could do is drop down another resample sop here, wire this into the Vellum solver, and then here, check resample by polygon edge, uncheck maximum segment length, and just check maximum segments. Set those to a number of 2 like this. So when I enable my points here, I just doubled my point count and also set this to subdivision curves, so I round them off a bit where I have jaggies in there. So all that's left to do is maybe write a color attribute on those individual primitives, which I can then use for shading, and then use the render engine of your choice to render this out. So when we look at this, again, rather easy setup, just creating 2 planes, scattering points on them, connecting them, then resampling those individual polylines we created, creating groups to pin the endpoints and animate them, then creating a single R-scale attribute per primitive, animating one of the ends to twist, setting up my constraints, and then in the constraints, reading out the rest length scale attribute that we created, promoting them to primitive, and then applying the rest length multiplier to the rest length itself, feed that back into the Vellum solver, and then finally just resample it. Let's attach a null, call this one out, and we are officially done. Simple twisted wires.